So check your graphs. The first graph has no, you can't see it here yet. The first graph has no asymptotes. And I'd like you to draw an open circle right there on your graph. Put arrowheads on the end. This introduces a graph with a hole in it. That's interesting. Yeah, depending on your window, you may or may not see the hole in your graph. But this graph does have a hole. One of the reasons they try to set up this window is that window will hopefully show holes in your graph. If it doesn't show a hole in your graph, try going zoom standard and see if you can see the hole in the graph. The next ones, the second one also has a hole in the graph. The third one has an asymptote right here at x equals 1. Later on, we'll also find out this one has a diagonal asymptote. Sound like fun? Same thing with this one. Has an asymptote there and a diagonal asymptote. And the last equation is another equation with a hole in it. You have to draw an open circle where there's a hole. The first one's on the first page. Yeah, I can go back to the first one here. Whoops, I can try to go back to the first one. There we go. So group 1. Group 1, did you notice that every single time you had a parabola on the top of some sort divided by a line on the bottom, you had something with a degree of 2, that's a parabola, divided by something with a degree of 1. When you have a parabola divided by a line, we get the following characteristics. Sometimes your graph has holes. And sometimes it has vertical asymptotes, and later we're going to learn about oblique asymptotes. Oblique is another word for diagonal. So what has happened in the past is whenever you had a non-permissible value, you had an asymptote. But in this case, sometimes we have asymptotes at our non-permissible value, and sometimes we have holes. So the question is, when do we have a hole, and when do we have an asymptote? So in the first equation, if I was looking at this first equation, ooh, I like that. Could I simplify that? How would I simplify it? Any ideas? You could you factor anything here? Yes, the top is a difference of squares. It's x plus 1, x minus 1. And on the bottom we have x plus 1. What does that mean? It cancels out, and the equation just becomes x minus 1. What kind of graph is x minus 1? A linear, straight line. What's our final graph? A straight line with a hole. Why does it have a hole? Because we still have a non-permissible value. Even though it cancels out, in the original equation, you're not allowed to plug in minus 1. So we have a hole in this graph at minus 1 comma something. Can someone tell me what the y coordinate of that hole is? It's on that line. What happens when you plug in -1 into the new equation? You get -2. That's the equation of the hole, because the graph simplifies to be something that we know, a straight line, which we can graph, but there's still a non-permissible value at -1. So we label that non-permissible value as -1, -2. But everything else is going to be on the line y equals x minus 1. The second equation also has a hole. Can we simplify this one? Can you factor the top? It would be x plus 2, x minus 1. And then the x plus 2's would simplify. We still have a non-permissible value at -2, but then the graph that we have is just the line y equals x minus 1, because that's what the equation becomes after it simplifies. Can someone tell me the y coordinate of my hole? -3. Plug in -2 for x, and now you would get -3. That's the coordinate of the hole. Notice in the third one, you can't simplify it. If the equation is something that you can't simplify, if your non-permissible factor doesn't go away, it's just like before, it stays an asymptote. Can you see in the third one that 1 is your non-permissible value? That's what would make you divide by 0. Yes? -2 is still your, if you look at your original equation, what would make you divide by 0? That would be the -2. So since in the third one it doesn't simplify, the non-permissible value stays as a vertical asymptote. In the fourth one, you can simplify that. You can factor the top as x plus 1, x plus 1, but the factors don't cancel out. So the non-permissible value of -2 stays a vertical asymptote. And finally, the last one, what can I factor out of the top? I can factor out a 2x, leaving me with x minus 2, and sure enough, that matches up perfectly with the x minus 2 on the bottom. As soon as your factor or your non-permissible value cancels out, it ends up being a hole. So the non-permissible value is 2. The hole is going to be at 2, comma. To find out the y coordinate, you look at your new equation. The new equation, after it's simplified, is y equals 2x, which is a straight line. And your hole is going to be at 2, comma 4. That's type 1, parabolas divided by lines. Type 1 ends up being either holes in your graph or vertical and oblique asymptotes. And now you're ready to go to group 2 and graph those ones. All right, so the first one has a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 3. This one has a horizontal asymptote at y equals 1 and vertical asymptotes at x equals -2 and x equals 2. And finally, we have vertical asymptote at x equals 1 and horizontal asymptote at y equals -2. So group 2, how do we characterize it? What are the different things that are part of this graph? And notice in group 2 that In the fraction, the degree is the same. Either you have a line divided by a line or a parabola divided by a parabola. Characteristics of these ones. Characteristics of these graphs is that we have horizontal and vertical asymptotes. The vertical asymptotes are exactly where our non-permissible values are. Which makes sense because none of these have any place where the bottom cancels out. Can we cancel out this x minus 1? No. In the second one you could factor. The top is a difference of squares. X plus 1, x minus 1. The bottom is a difference of squares. X plus 2, x minus 2. Does anything cancel out? No. The third one, you could factor out a negative 2, leaving you with x minus 2. But still, no factors cancel out. Only when factors cancel out do we get a whole. So when the degrees are the same and nothing cancels out, you will always have your vertical asymptotes at your non-permissible values, just like you had in the past. So that part's easy. But now we have new horizontal asymptotes. In grade 11, your horizontal asymptotes, if you had them, were always at y equals 0. Okay? Now they're at a different place. How do you find out where that different place is going to be? Remember that horizontal asymptotes show what happens when x gets very, very big. Okay? So I'd like to use an analogy here, because on the bottom of this first fraction we have x minus 1. Okay? If you have $1 and you lose $1, that's a big deal, right? Yeah, that sucks. But if you have $500 and you lose $1, still sucks. If you have $1 billion and you lose $1, you're like, yeah, whatever, right? It's like when if you've played Monopoly at the beginning of the game, if they land on something and the rent is $2, you're like, pay up. You're like, I need that money, right? At the end of the game, they land on something and it's $2 and you got hotels on Boardwalk. You're like, you know, don't worry about the $2. Let's not waste our time at the end of the game, right? And so when x gets really, really big, subtracting that 1 doesn't really make that much of a difference. If I put in 1,000,000 for x, I would have 3 million over 1,000,000 minus 1, which is basically really close to 1,000,000, right? What is 3 million divided by 1,000,000? Close to. Well, 3 million divided by 1,000,000 is going to be 3. 3 million divided by something that's really, really close to 1,000,000 is going to be really, really close to 3. So what we can do when we're trying to figure out the horizontal asymptotes is we can look at the equation and just look at the values of the highest degree. The highest degree in the top is an x to the 1. The highest degree in the bottom is an x to the 1. And if I just look at the x's, I have 3x on the top and x on the bottom. What does that simplify to? Y equals 3. And that's how you can find your new horizontal asymptotes. All right? If you have a big number and you square it, is subtracting 1 going to make a big difference? No. If we just look at the highest degree on the top, my highest degree is an x squared. I have 1 of them. My highest degree on the bottom is an x squared. I have 1 of them. What would you get if you did x squared divided by x squared? 1. And that's the equation of your horizontal asymptote. In the last one, your highest degree is an x. In my numerator, I have a negative 2x. In my denominator, I have an x. If I simplify that, it becomes negative 2. So finding your horizontal asymptotes can be done by looking at your highest degree. group 3. So the last group, we have in each of these, the degree is larger in the numerator, in the denominator. So we have a constant over a parabola, or we have a line over a parabola. But the key thing is the bigger degree is in your denominator. We'll draw asymptotes in where applicable. Asymptote at 0, asymptote at 0, 2 asymptotes there, asymptote at 0, asymptote at 0, and asymptote at 0 and 0, and an asymptote at 0. Oh, this is an interesting one. Even though the graph goes through the asymptote. No hole. We're gonna, okay. So we'll have some discussion about the last one. It follows the rules. So, characteristics. When the degree is larger in the numerator, your characteristic always, there we go. You will always have a horizontal asymptote at y equals 0. So the degree is bigger in the denominator. All these, our horizontal asymptote is always y equals 0. You could even use the same thing we used in the previous one. If you look at the entire fraction, what's the biggest degree? X squared. We have 1x squared on the bottom. How many x squareds do we have in our numerator? None. So I could write 0x squared. If I simplify 0x squared over x squared, what do I get? 0. And my asymptote's at y equals 0. So you could use that same strategy we used to find the other horizontal asymptotes to find each of these horizontal asymptotes. So the second one you could factor the bottom to be negative x plus 1, no, minus 1, sorry. Negative x minus 1 and x minus 3. And then you have issues with the last one, because the last one does go through an asymptote there. There is no hole. It has the point 0, 0. In fact, if you plug in 0 for x and simplify this, can you see that you would get 0, 0? So the question becomes, how can our graph go through an asymptote? Well, first of all, we have to remember that horizontal asymptotes don't say things about non-permissible values. Horizontal asymptotes say things about when x gets really big, either big positive numbers or big negative numbers. And as x gets really, really big, in this case, the top would become 4 times a million if x was a million. On the bottom, you would have a million squared plus 1. And the bottom gets bigger much faster than the top gets bigger. So it does approach 0, but that asymptote just shows what happens at extremes. And so it is possible for a graph to go through a horizontal asymptote in the middle. So our job in the next part of this unit is going to learn how do we graph all of these without a calculator and show the characteristics.